Welcome back. Thank you for doing our break a little bit offset from the other group, and still no coffee. So hopefully craft time will keep us awake and energized for the last hour here. This goes until 5:30, right? Yeah, okay, great. All right, so yeah, so everybody take a straw and pass it on. In your little craft pack here, there's a compostable straw and two, what is it called? Pipe cleaners. What I'm going to ask you to do, we're going to make a flame. So you're going to take the pipe cleaner like an inch off the bottom of the straw and wrap it around the bottom of the straw. And then you want to wrap the same length on the other side so that it kind of looks like what we were just looking at. Right? So my terrible PowerPoint art is going to come to life here in our graphs. All right, and as everybody's getting their straws, we're going to look at this little dude. So like Professor Law said, I was from the first version of this summer school, and my friends and I still refer to it as summer camp, combustion summer camp. But so I thought, what better for summer camp than to have a craft component of the meeting. All right. Being very choosy on colors. I almost went with, there were ones, my husband and I were standing in Michael's a couple days ago, taking out pipe cleaners. And I almost went with super sparkly ones, but he correctly said that they would probably get sparkles everywhere. I don't think everybody needs glitter on their stuff, so we just went with fluorescent instead. All right. So most people have straws. So just as a quick review, right? So if your straws go like this, right? We have what we should do is have like another one that points normal, but you can visualize the normal to your pipe cleaner here. So this is either a low velocity flow or a high flame speed flame, right? It's all relative, this kinematic condition. But for a given flame speed, as I increase the velocity, my flame angle is going to look like this, right? Okay. So now we're going to do a couple thought experiments with a quick sidebar, which I'm going to do under the thing here so that I don't have to put it back up. But let's explore what's going to happen to our straws here when you vary the velocity very slowly, right? So what we're going to do is we're going to have some mean flow velocity, so your straws or your pipe cleaners are going to start at a particular angle. And then very, 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 very slowly, you're going to have a sine or cosine wave that changes the incoming flow speed, right? And so if I'm going to draw, everybody remembers what a cosine looks like, right? Right, so it starts high, and then as the flow velocity gets lower, your flame's going to go out, and then as it gets higher again, your flame's going to go up, and it goes out and up, right? So this is going to happen very slowly because I've told you right now that the frequency, omega, that we're oscillating this at is very low. Typically, however, the oscillation frequencies in real devices, if it's not, a paper mill package furnace, are on the order of hundreds, if not thousands of hertz. And so the oscillations are not going to be slow compared to timescales associated with the flame. And so instead, we have to think about what happens when now the wavelength of the disturbance becomes similar to the wavelength or the length of the flame, which is the length of your, what are these called? Pipe cleaners. See, I was really counting on that coffee. All right, the length of these pipe cleaners going forward. So we're going to do a quick sidebar. Before, we talked about acoustic wavelength. And acoustic wavelength lambda was equal to C over F, where C is your speed of sound and F is the frequency at which the oscillation oscillates, or the frequency of the sound wave. You can apply this to anything, right? And so now I'm going to introduce the concept of convective wavelength. Which we typically call lambda sub C, because let's just use C for everything. Lambda sub C is now the convective velocity over the frequency of the oscillation, right? So what we've changed here is not the concept of frequency, just the speed at which the wave travels. You can, I should have put a picture in here, but you can see a really good example of convective wavelength in flow separation off of an edge, particularly the Kelvin-Helmholtz instability, right? So if you have high velocity, low velocity, you end up with something like this, right? This nice periodic vortex shedding. So you've got the vortex centers and the vortex braids in between. These are moving downstream. There is some bulk flow velocity, but then there is some convective velocity at which these travel downstream. And I can define from vortex center to vortex center the convective wavelength of this instability, and then I could define the frequency at which it's happening, which would be the convective wave, or the convective velocity over the convective wavelength. In flows like this, interestingly, this isn't always the mean flow velocity. Sometimes it can be anywhere from half to 1.5 times the mean flow velocity, depending on the situation. And there's some really good fluid mechanic work that talks about this. This is just a nice visualization because I think most people have seen these separating flows before. But when I was talking about equivalence ratio fluctuations, where somewhere upstream in your fuel injector, right, you have fuel that's pulsing. Now if you think about it, you have some variation in equivalence ratio, and the speed at which that equivalence ratio disturbance convects downstream is its convective velocity. And so there's a wavelength associated with that equivalence ratio wave as it moves downstream, right? And so just wanted to make sure that that was clear, especially for folks who aren't used to thinking about acoustics. We've got the acoustic wavelength and the convective wavelength. If you have some acoustic fluctuation that's driving your vortical fluctuation, which is a very common situation in combustors, they're going to happen at the same frequency, right? So if I have 400 hertz, I was about to spell this out, 400 hertz forcing, I'm going to get a 400 hertz response in the shear layer, and tomorrow we'll talk about why. But the wavelength of those two waves are going to be really different because the convective velocity is really different. In a combustor, let's say the flow velocity is 50 meters per second, and this is at standard temperature and pressure, 340, can be much higher at combustor temperatures, right? This goes to the square root of temperature. And so what ends up happening then is that typically acoustic wavelengths are much longer than convective wavelengths. And so in my PhD work, I didn't just choose 400 hertz randomly. I did a lot of work at 400 hertz. When I was a grad student, the wavelength of a 400 hertz wave is a little over a meter. That's its acoustic wavelength. Convective wavelength at the velocities I was looking at was about, this long, right? And so the difference between your acoustic and your convective wavelength becomes important, as you'll see in a second. Okay, questions on acoustic wavelength? Everybody cool with this idea of a convective wavelength, convective velocity? All right, good. All right, back to pipe cleaners. Sidebar over. Okay, so now, going back to our pipe cleaners. When we had this varying very slowly, it was because if the frequency was very low, the convective wavelength was very high. And so if this is our flame length here, let's say our convective wavelength was extremely long. And so if I'm the flame and I'm this tall and I see a disturbance coming at me whose wavelength is 10, 100 times my length, I don't really notice that there's some variation along it, right? I just breathe with the wavelength. But now, if a disturbance comes along where the convective wavelength is shorter than the flame, now the flame notices that there's a difference, right? And so if we think what happens, and this is where the pipe cleaners are going to be useful, if I see some disturbance come up here, first it's going to hit the bottom of the flame, and it's going to bend the flame up. But the rest of the flame doesn't know yet that a convective disturbance has hit because the wavelength's very short. And then you have, because now your flame is responding to that disturbance, the normal has changed, you still have this tangential velocity, and so what ends up happening is this is where doing it in front of a classroom is not going to be all that graceful. This wrinkle now propagates along the flame at that tangential velocity speed. That tangential velocity is dependent on the mean flame angle, right? The flame angle that you get from that U-bar. And while this is propagating along, this guy down here has hit the bottom of the sine wave or cosine wave or whatever. And so now I have a bend in the other direction, right? And I really should be doing this on both sides, but that feels like a little bit too much for me right now. And so now you can see I have a wrinkle in the flame that's going to propagate down at that tangential velocity, and it wrinkles in, what would this be? A negative curvature up here and a positive curvature down here. And then this structure is going to convect downstream. It's going to convect downstream. And then eventually, when I get to the next wavelength, it's going to happen all over again. Oh God, guys. Here we go. So now, you should be following along with your pipe cleaners. This is why I gave you all pipe cleaners. So now if I keep going, I'm going to cheat. I'm not going to do it this way. Now if I keep going, I'm going to end up with a flame shape that looks like this, right? And if I'm doing this symmetrically, then I'm going to end up with that flame shape on both sides. There we go. Right? And so now I have this oscillation in the flame area, and we'll talk about how that comes up in just a second, where the area term comes from. But this is how disturbances convect along the flame. One of the key pieces here is the fact that the flame is pinned to your compostable straw, right? If the flame didn't have an attachment point, it could just flap around, right? And so actually some of the very best work that I've seen on this is not having a flow velocity that fluctuates, but having a flame holder that fluctuates. And you can get the same effect because now you've displaced the flame in a steady flow and you get this nice convective behavior. Okay. All right, so now we've got some oscillations along the flame. Now, let's imagine the wavelength is very small. So now we have lots of bends in our flame, right? And so now we have very high curvatures. All the time, and this is one thing I couldn't figure out how to do with pipe cleaners, all the time is the flame is propagating normal to itself. And so as these wrinkles are propagating downstream, they're not going to stay the same size. They're going to start changing shape because the flame is always propagating normal to itself. And one thing you can see is, so the reactants are over here, so inside these negative curvature regions, you've got a pocket of reactants, and so those are starting to close in on themselves. And then in these positive curvature regions, the flame's propagating outwards, right, into those, you know, either side little pockets or cusps, which is what they're called. And this is really beautifully demonstrated in this paper by my academic sibling, Dong-Hyuk Shin. He was a brilliant theoretician, is a brilliant theoretician. He's a professor at KAIST in South Korea. And this diagram really nicely shows what's happening. And so in this simulation, what he did was he started with a flame. It had a sinusoidal wrinkle in it, and then he just let it propagate, where everywhere on the flame was propagating at the same speed, SL naught. And he looked at where the flame, each location on the flame was after a given time t. And, you know, it's propagating out from itself, so these circles are sort of these fronts of propagation. But in these regions of negative curvature, because this thing's propagating into itself, it forms a cusp, and that cusp really rapidly decreases the flame area as compared to the positively curved places where they just grow. You can see this. This is another, now this was just a freely propagating flame. This is now on a flame holder. And here, he's moving the flame holder back and forth, which is sort of the first step to understanding what's going on as compared to having a fluctuating flow. And by moving the flame back and forth, he's displacing it. And what he's plotting here is a function of downstream distance, is the oscillation in the flame. So initially, you have these nice sinusoidal waves, but as these negatively curved regions propagate in on each other, you start to destroy flame area, and you do so nonlinearly. So if you remember, so this is the flame fluctuation as a function of downstream distance. You can see, if this is the time average flame location, you can see these lines for the baseline frequency, a higher frequency, and an even higher frequency, omega, 2 times omega, and 3 times omega. And you can see that the displacement is much less because these wrinkles get smaller, and so they propagate in on themselves more quickly. This cusp formation and propagation process is the fundamental nonlinearity that drives the saturation we saw in that gain curve, right? So we had the damping curve and the gain curve. Even in a perfectly laminar flame without any turbulence or swirl or any of those other things that could cause other sources of nonlinearity, you will always get nonlinear saturation because of this cusping phenomenon, which is pretty neat. Okay, so how does this lead to area fluctuations? Well, I thought about how to do this with pipe cleaners, and then I was like, this craft is getting out of control, guys. Really what you need to do is you need to put some boundary conditions on it. So imagine we had this craft, but now the flame, it was in a tube, and the flame basically got annihilated every time it hit the wall, right? It quenched. You can imagine, even as the flame breathes without all these wrinkles in it, you're going to have a fluctuating flame area as this flame runs up and down the wall. Here it's going to be shorter, and so low area. Here it's going to be longer, and so high area. And so you're going to get a fluctuating velocity that way. And now when you put wrinkles on it, you end up with even more severe interactions. Or, so this is a wedge flame, or you could do it in a cone flame, where now you have two boundary conditions. You're held to the wall down here, and you've got this point up here where the flames have to stay attached. And so now you have even more severe fluctuations as a result. There's some math that describes this, and that's what we're going to do for the rest of today. But I want to make sure folks conceptually understand this before we go back to the board for a little while. In particular, that this is clear and why this propagation is nonlinear. Questions, thoughts, comments? Unhappy with your pipe cleaner color choice? I know it's the end of a very long day. Okay. Good stuff. All right. So there is math that some folks use that I wish more folks used to describe this, and it's called the level set formulation. So while I get this going, level sets aren't just used in flame response. Show of hands, who's heard of level sets before? A few people. Okay, probably simulation people. They're used very commonly in two-phase simulations. So if you do droplet work, using a level set is a pretty common way of tracking your droplet surface. They're used in a bunch of situations, but they're particularly good for flames. And the goal of this analysis is not to faithfully model flame response in all its all its gory detail. You can do this for turbulent flames. You'll see once we get to the end that there's a big problem here in the way that we do this. But the goal here is to outline some fundamental theory to understand how flame kinematics drives heat release rate fluctuations, so that when we look at flame response, and that's what we're going to start with tomorrow, you can understand where those disturbances are coming from. And so that's the goal here. It's understanding. It's not faithful modeling of every single detail. So that means we're going to have some assumptions. These are the big ones, not all of them. We're going to assume that we have a connected flame. So we're not tearing it at any point. The flame is infinitely thin, so that we can treat it as a level. So basically what we're saying is the flame thickness is so much thinner than any length scale in the flow that the flow can't tell that the flame's there, or that it has any size. And for now, we're going to say the SL is constant along the entire flame. 1 and 3 can pretty easily be relaxed, and I can give you a bunch of papers that talk about pocket formation and stretch effects. But for now, in our last 45 minutes here, let's not go too nuts. All right, so basically what we're going to do is we're going to define a field. And this field I'm going to call G. It's a function of space and time. And what I want to track in that field is just one level, or one isocontour. And you can set it to be anything. It's just really convenient when you set it to 0, right? It can be 2. It doesn't matter. You just got to track one level of the field. And incidentally, the rest of the field doesn't have to be defined, which is kind of fun. Or it doesn't have to be uniquely defined. So what I'm going to say is that my flame sits at this contour, G equals 0. And so I need some way of describing the motion of this level in a flow field, and that's going to help me figure out what's going on with the flame. So if we remember, flames propagate normal to themselves, so I can define my normal vector n hat. This is not a Fourier transform, that's just the normal vector. And that's going to be negative grad g times the absolute value of grad g, which, if anybody remembers vector calculus, should look somewhat familiar. Okay, so now what we're going to consider is I have some flame surface, and these are the reactants, and these are the products. So we're looking at premixed flames only. Although you can do this for non-premixed flames, you don't track a flame surface, you track a mixture fraction, and I can give you references on that if you're interested. At each location in the flame, there's a flame normal, and the flame is traveling at some speed SL naught, normal to itself. And we have an incoming flow field, U of x and t, that we have defined. One of the major drawbacks of a formulation like this is that we look at how the disturbance field affects the flame, but you could pretty easily imagine, because the flame is dilative, that the flame affects the velocity field too. But that's not captured in these methods without a whole lot of hassle. And so most people don't do it. So this is not what's called the two-way coupling problem, it's the one-way coupling problem. We're just looking at the response of the flame to incoming disturbances. But hey, you know what? That's like still really useful. But this is the major drawback, and I cannot tell you how many times I have seen reviews, papers like, well, you don't have two-way coupling. Like, no, we don't. Okay, not bitter at all. Cool. So now I have this surface in this flow field, and I want to see how it propagates, right? So I'm going to write down an advection equation, because that's what we do. So I'm going to start with the time dependence of g, and I'm going to say u dot del g. There we go. So that's an advection equation. If the flame was a completely passive surface, then that big U, let me put a vector on that big U, that big U would just be the incoming flow field, and we'd be done. And what we would do is we would look at the advection of the surface G in the flow field U, and that would be kind of boring. Instead, what makes these methods pretty interesting for flames is that there's another velocity component here, which is the flame propagating normal to itself. So let me write that out. If SL naught equaled 0, then big U would equal little u, and we just have an advection problem. But that's not the case. SL naught is greater than 0, so the flame is propagating. And so what we care about is the flame propagation normal to itself. And so we have to look at how U compares with the direction of the flame. So we've got some dot product action going, right? Because this is going to determine how that surface moves. And so that's now equal to SL naught plus U at that surface location dot n. So now we have two components of that velocity. There's the incoming flow, and there's the fact that the flame is propagating normal to itself. Does that make sense? Again, vectors, super fun. Okay. So now what you want to do is shove this back in here. Typically, the first thing we do before we go any farther is some fun non-dimensionalization, because it's just good practice. So I'm going to non-dimensionalize a bunch of stuff. I'm going to say SL tilde is equal to SL over SL naught. One would do this if you wanted to apply stretch corrections. in most cases. In our assumption set here, this is always just going to be 1. U tilde is equal to U divided by SL naught. That feels like a good thing to do. X tilde is going to be X divided by some hydrodynamic length, which could be your, your straw diameter or something, your convective wavelength, pick something meaningful. And then pour time just gets non-dimensionalized by everything else we already have. And so if you do all the non-dimensionalization, you shove this piece into this piece, you end up with what people refer to as the G equation plus is equal to SL tilde. Right there. So that all came in because, remember our definition of the normal over here. So this is the equation that describes the motion of that premixed flame front that's connected infinitely thin and at constant velocity in whatever field you give it, which is pretty neat. Turns out solving this equation is really hard. It's not simple math. And that paper that I showed you before from Dong-Hyuk Shin actually went ahead. He had found kind of a nifty way to do it for freely propagating flames. But when you have boundary conditions, and as we saw, the boundary conditions are quite important, it gets pretty difficult. And so we reformulate the problem a little bit to be able to do it. Any questions before we go to that reformulation? Everybody see what we're trying to do here? Cool. All right. All right. So, the reformulation. So what I'm going to do, just like our pipe cleaner experiment here, I'm going to have our straw, and I'm going to have our flame, except I want it to be a dotted line. We're going to have our flame sitting at some base angle here that is determined. So I have my incoming velocity field, U of X and T, whatever. And so that base angle, or that time average angle, is dependent on the time average velocity of this field. But because we want things to be interesting, we're going to start to vary the field, right, with a harmonic function, just like we did with our pipe cleaners. So instead of putting this in a Cartesian coordinate system, which we're going to do when we go back to the slides in a second, the first thing I'm going to do is just draw a coordinate system along the flame, because that feels a little bit easier. So capital X and capital Y are the coordinate system along the flame. And then as I, fluctuate this, so now I have plus epsilon cosine omega t or whatever. Now I have some flame fluctuation along that mean. So now, instead of tracking this as some random thing in space, I'm going to say, well, I already have this coordinate system, so I'm going to look at the deviation of the flame relative to this coordinate system. And to stay consistent with the reference I'm about to give for this, I'm going to call this xi. Is that xi? Zeta? Which one's the squiggly one? C. That's it. Okay. And this is going to be function of just x and t, right? So we've defined this relative to that big X and time. And so if you wanted to do this with your pipe cleaners, this is where you could see this would form and propagate downstream, right? And I'd have some wrinkle that moved along with it. So now I can reformulate my velocity field here. I can have ut, which is the tangential velocity in the x direction. And that's the speed at which the disturbances are going to propagate along the flame. I could also define un. This is the normal velocity, which by definition is going to be my SL naught under my assumption set. And then I have some velocity fluctuation coming in, and the flame's going to respond based on that. Okay, cool. So if I rewrite that equation in the same spirit, but now for psi squiggly here, I end up with something that looks like this, squiggly dt, ut d psi dx, right? Because we're only advecting in the x direction, is equal to u prime of x and t, where I forgot to define u prime, sorry. This is now the disturbance velocity. So same idea as that guy up there. We've just put it in a form that only has to go in one direction, which is much easier. Okay. Now if I'm going to solve this, right, so this is a partial differential equation. So the first thing I could do is I could solve for this, right, and I'd end up with some integrals on the right. But I have a forcing function here, which means that when I'm solving this differential equation, I end up with two solutions. For people who do this regularly, they're like, yeah, O'Connor, whatever. For people who haven't reached back into differential equations, you have the homogeneous solution, and you have the particular solution. The homogeneous solution is what happens when this is 0 and is defined or is generated by your boundary conditions. What's our boundary condition here? What did I say up there? We're connected and we're stuck to our straw, right? And so if this was freely propagating, this could like move around. But because the bottom of the pipe cleaner is stuck to the straw, it can't move around. Just like the jump rope before, you enforce some boundary condition, and that's going to determine the form of your homogeneous solution. And then the particular solution is determined by this forcing function or your disturbance field. And so now, if you want to look at the dynamics of the flame at any location in time, what this equation is telling you is that the disturbance amplitude is the sum of two effects. One is the local normal velocity fluctuation to the flame, which the flame always feels at a particular location. But the other is the wave that has propagated from the bottom because of the boundary condition. And so you can imagine that depending on the mean flow velocity and the wavelength and that tangential velocity, right, a lot of different things, that you could have regions where these two disturbances constructively interfered or destructively interfered. And we're going to see this in our flame response discussion tomorrow. But this is like a big freaking deal. The fact that I have one disturbance, that incoming disturbance that turns into two disturbances on the flame is so crucial. This one right here, the boundary condition, is often called either the base wave or the root wave. And then this is the local response. Non-local and local. And I cannot tell you the number of times that I've seen people focus only on the local response without remembering that pinning your flame to a boundary condition creates a non-local response. And we're going to see that effect in several of the examples we're going to do later. Questions on this? This, like, when I finally understood this, granted this was my thesis, so for the 4 of you who are doing actual thermoacoustics, your mind should just be like, right now, right? But this explains so much, and all comes out of, again, a pretty simple set of assumptions, but helps us understand what's going on. Okay, so let's look at some data that helps explain this better. Wait for this to start again. One thing that's really interesting, right, now that I've like harped on this boundary condition jazz for a while, is what happens when you don't have a boundary condition. So the dynamics of lifted flames, where like, I don't have another pipe cleaner, but imagine I just had a lifted flame that didn't have a boundary condition. The dynamics are really different. You can still do this, right? But now you have all local disturbance effects, and that sort of makes things interesting. The cleaner looks really sad. I chose orange for Princeton. Okay. Come on thing, let's do this. All right, great. So this comes from a paper that was written by Tim Lewin right at the beginning of his faculty career. He was a theoretician first and then started doing experiments, if you can believe it. But this is a nice paper, and so one of the things about the thing that I showed you doing it this way is that if you change the mean flow, which you'd want to do in a parameter sweep or something, you have to keep changing your axis, and that makes comparison of cases with different mean flows a little bit wonky. And so what he did was he moved to a slightly different way of showing this, right? So now it's not psi, it's whatever this guy is. I should learn my Greek letters before I come back tomorrow. And now it's the location. Now we're in a Cartesian coordinate system that goes along with the flow. So flow is coming from the bottom, x direction downstream, r direction downstream, and then, x direction downstream and r direction on the cross. And at each radial location, you have some fluctuation, squiggly, as a function of r and t. So this is the wedge flame that we made with our pipe cleaners. You can also do this in a cone flame just as easily. You just have the boundary conditions backwards. And so now you have 2 non-dimensional quantities that are pretty useful. This U naught versus SL, this tells you your flame angle, right? This is you meeting the kinematic condition on the steady flame. And then beta is basically the aspect ratio. And so if you wanted to change the flame shape, the quickest way to do it in the equations is beta. Okay, everybody kind of got the shape down? Make sense? All right, so then what's in these results are basically just playing around with a bunch of different non-dimensional numbers. Epsilon, like we drew it on a board you can't see anymore, the disturbance is u bar plus epsilon cosine of omega t, right? So epsilon is the amplitude of the disturbance, and he defines some epsilon max just to be able to non-dimensionalize it. The other non-dimensional parameter you'll see here is the Struhal number. That's a non-dimensional frequency. And so that's some frequency, I think, times the flame length divided by the mean flow velocity u naught. Okay, and so we're going to step through each of these plots and kind of understand for the 2 different flame shapes what's going on. and how, as we change the frequency of input oscillation and the amplitude of input oscillation, it affects the flame kinematics. So the first plot is the dependence of the lowest velocity amplitude at which flame front cusps are present on Struhal number. So this one is not the best to start with, but let's just remind ourselves what's going on here. So flame cusping is this thing, right? And so within this flame length, the higher amplitude oscillation you create, the faster cusping happens as that disturbance moves along the length. And so if you have a very low amplitude oscillation, you're not going to cusp as fast. If you have a higher, because that curvature is higher, you can annihilate that flame faster. It's also going to depend on the beta, right? Because that's not only going to determine how your flame is propagating into the mean flow by this U0 over SL, but it also determines the tangential velocity of those wrinkles along the edge, right? Because it determines your tangential direction. So, I'm stepping on the computer stuff here. All right. So what we see in these cases, sorry, these are my cheat sheets here. Dependence of lowest velocity amplitude at which flame front cusp as a function of Struhal number. So as you increase the flame angle, and so, or the flame aspect ratio, that's what I'm looking for, that means that the flame length is higher relative to its width, right? And so that means the flame gets taller. And so you can go to higher amplitudes before you start cusping for a couple of reasons. One, the tangential velocity is faster because your flame is, further aligned with the mean flow velocity. But also your normal velocity, you're not creating for a given epsilon the same level of wrinkles as you are just because of the angle relative to the mean flow, right? And so you need, for a given Struhal number, you need a higher flame angle, or you need a higher amplitude for a higher flame angle in order to get those things to happen. Okay, this one's a little bit more intuitive. So graph 2 and 3, what's going on? Well, we'll just look at them. Okay, so graph 2, this is for a wedge flame at beta equals 1. So this is an aspect ratio of 1. So this guy's at like 45 degrees. And this is the resulting area fluctuation for an axisymmetric wedge flames as a function of the amplitude for a bunch of different Struhal numbers. So let's just take one frequency and look at these things, right? This is the nonlinear behavior we were looking at with that driving and damping curve, right? If I have small fluctuations, this is the linear result, right? If the flame was perfectly linear, you'd have increasing area fluctuations as you increase the input velocity or the input velocity fluctuation amplitude. But because of this cusping process, you end up forming cusps and destroying flame area faster as you increase the amplitude. That effect is faster, or you get the nonlinear rollover faster for higher Struhal numbers, because now you have tiny little, right, higher Struhal numbers, higher frequency, which means shorter convective wavelength. Now you have all these tiny little fluctuations on the flame instead of bigger ones, right? And all these tiny little guys are going to cusp out and destroy themselves faster than these lower frequency ones. So this is really the plot I should have started with, but this is exactly, that nonlinearity that drives you towards that Libet cycle. Just, again, these are laminar flames, super simple situation, just from the kinematics and the effect of cusping. You get that even more significantly for cone flames, and that's because for a cone flame, I don't want to take this apart. For a cone flame, you've got the top constrained, right? We've said this is a connected flame and that there are no pockets yet. Although if you really haul on this and you let the formulation do it, you can track pockets, not a problem. But here, the system's much more linear, and that's because you don't have this length, right, for all this to occur, right? And so you don't have the degrees of freedom, you could think about it, for all this flame motion that you do on the wedge flame. Okay, so this goes back to the wedge flame, and so now what this is looking at is not Struhal number, so this is for a given Struhal number, but now this is varying flame angle. And so again, on the x-axis is the amplitude of the disturbance, and we're looking at the resulting flame area. And as you increase B, where it goes up, it becomes more linear, right? So let's look at low B, which is when your flame is really wide. Now, because the normal component is much closer to the incoming flow velocity, you end up with these wrinkles, and the transverse velocity is a lot slower, so those wrinkles are going to propagate slower, so they're just lasting longer, and that gives them more time to cusp out and destroy the flame, and so you end up with a much stronger nonlinearity when you have a really wide flame like this. When it's really tall, which is up here, close to linear result, now for a given epsilon, because your epsilon fluctuation is less aligned, let's say that, less aligned with the normal of your flame, your disturbances aren't going to be as significant, they're going to propagate faster, and so, bless you, and so you're going to end up with wrinkles that more slowly cusp out and cause nonlinearities, and so your solution will be much, much closer to the linear result. This is a great paper. I highly, even if you don't read the paper, just spend some time, particularly with the top right and these two bottom slides or charts, play around with your pipe cleaner to kind of figure out what's going on with that. So, key point. One of the cool things that comes out of this is that flames act as low-pass filters, right? Because as you, and that really comes out in this plot on the top right, as you increase the frequency, you're basically increasing the level of curvature, which just allows these flames to burn out these cusps faster. And so you basically don't allow that level of, or the same types of area fluctuations for as long. And so there is a certain frequency at which, the flame just propagates too fast for those disturbances. And so this is a fun feature. When we look at frequency response of flames tomorrow, this is going to become quite evident. The frequency at which it stops responding and its robustness to stretch, which we haven't talked about, but we can talk about more tomorrow if folks are interested, really determines what the frequency response is and where nonlinearity kicks in, which, as we saw before, is really important for determining the limit cycle amplitude of the oscillation. So, with that, we are close to done. We got 10 minutes. And I timed this shockingly well. What have we learned so far? Hopefully, we have identified the technologies in which combustion instability is an issue, put a flame in a box that can resonate, and you could have combustion instability. You might not necessarily, because the phase has to line up, and that has to do with the basic thermoacoustic coupling process. We talked a lot about phase. And hopefully, with our pipe cleaner example here, we've also explained the kinematics of flame response to at least harmonic inputs that help us understand where the nonlinearity comes from, and that there are going to be multiple disturbances on the flame, and that's going to determine the overall global response, which is something we'll talk about more tomorrow. Okay, that's what I had for today. Any wrap-up questions before we call it, and we'll pick up tomorrow on any of this. Doesn't have to be on kinematics, it could be on whatever. Silence. It's been a long day, hasn't it? Yeah, that's cool.
Rewarding.
Good. You got a craft out of it. All right, so as a quick reminder, tomorrow we're talking about flame response and flame transfer functions. So now we're gonna put all this knowledge into action. And then we're gonna talk about instability control. And then there are gonna be advanced topics. There are 3 of them that I wanted to quickly mention, but then I'm gonna ask you folks what you wanna talk about. I've left what I think is some time at the end to just talk about stuff you're interested in. So hopefully the basics today have triggered some thoughts. Shouldn't use the word triggered. You'll see why tomorrow. Has a really specific meaning in instability. Has, percolated some thoughts. As we talk more tomorrow, jot some things down, because we'll freeform it at the end, and I want to see what you're all interested in and see if we can answer some questions on that. Sound good? Okay. Bring your craft back tomorrow, because we're going to use this some more. If I could have the extra crafts, and somebody has a copy of Chu and Kavazne, I would like that back, and I will see you all tomorrow. Okay.